One of the applications of friction is in the use of wedges for mechanical advantage. Here the idea is that we can apply a smaller force to lift a larger force under the right conditions. In this example, we want to calculate the force P required to level an I-beam. Part A asks us to find the force P required to do the leveling, and Part B asks us to determine whether or not the wedge will stay in place once we remove the force P. We can address the second part of the problem by asking for a force, I'll call it R, to pull the wedge out. If this value turns out to be positive, then we have to exert a load to reverse the process, and the wedge will stay in place after we remove the force P. This phenomena of a mechanical element staying in place due to friction after the driving force is removed is called self-locking. This is an important feature of many fasteners. Let's now take a look at the solution. One of the things to note about the figure shown on the previous slide is that there are no dimensions given for the wedge, so we will treat this as a particle problem. We're pushing in with force P, and we're going to get resistance to the wedge moving in both from above and below. The problem statement has a 1,000 pound beam whose load is going to be equally supported at C and D. So from the top we're going to have a 500 pound force, and as we're pushing in we're going to get resistance to that. So we're on the threshold of sliding if we're pushing this in. So this force up here is going to be the friction coefficient times 500 pounds. From the bottom, we don't yet know what this force Q will be. It's a normal force to that 6-degree incline, and we're also sliding on the bottom here, so I will also represent this friction force as mu times Q. So if we're treating this wedge as a particle, it only has one motion translation. If it's slipping above, it's also slipping below, and so we have simultaneous slip on both surfaces. Because we're treating this as a particle, then we'll just have force equilibrium equations, so we'll write sum of the forces in x equals 0 and sum of the forces in y equals 0. And in x we have q sine of 6 degrees plus the friction coefficient times q cosine of 6 degrees plus mu times 500 pounds minus p equals 0. And in y we have q cosine 6 degrees minus friction coefficient times q sine 6 degrees minus 500 pounds equals 0. So from the second equation we can solve for q, and that turns out to be equal to 500 pounds over cosine of 6 degrees minus 0.3 sine of 6 degrees, and that number turns out to be equal to 519.1 pounds, so slightly larger than the 500 pounds acting from above. The value for P then we can take by just using the x equilibrium equation and substituting in this value for Q, and we do that, we get these numbers, and we add all that up and we get 359.1 pounds. Part B of the problem asks if the wedge will stay in place once we remove the force P. And the easiest way to think about this is to ask if we apply a force R to pull this out, will R have to be positive in order to cause motion to occur? So we still have a 500 pound force from half the I-beam up here, but now we're trying to slide the wedge out in the opposite direction, so the friction force is opposing that, mu times 500 pounds. We'll generally now have a different force N from the bottom, a different normal force, so I'll give that a different label. That's also sliding, mu times N. And the question is, do we need R to be greater than 0? And if the answer is yes, then it's self-locking, and if the answer is no, then it's capable of sliding out by itself. Once again, we're using our particle equilibrium equations, so we'll have sum of the forces in x equals 0 and sum of the forces in y equals 0. And in x we have r minus mu times 500 pounds minus mu n cosine 6 degrees plus n sine 6 degrees equals 0. And in the y direction, we have n cosine 6 degrees plus mu n sine 6 degrees minus 500 pounds equals 0. So once again, we can use the vertical equilibrium equation to solve for the normal force N. This turns out to be a little less than 500 pounds now. If we plug the numbers in, this number turns out to be 487.4 pounds. And if we take the results and put them back in to solve for R, we get these numbers, and the result is 244.5 pounds. Our result is that we have to pull the wedge out to cause slip in the other direction, so the wedge will stay in place, and that makes this system self-locking. Before leaving this topic, I wanted to shed a little more light on the topic of self-locking in fasteners. This problem is idealized by taking one complete revolution of a threaded fastener and unwinding it. In this geometry, the parameter L is called the lead. This is the axial distance a fastener advances in one complete revolution. You can see that the horizontal distance in this figure is the circumference of the fastener based on the mean diameter between the root and tip of its threads. The angle psi measures the helical pitch of the fastener. In this case, the force F is the load we're trying to lift, or the axial force we're applying along the long axis of a screwdriver. The force P is a circumferential force needed to lift the load or tighten the fastener. We can take F as a known quantity, and then we have two unknowns, the normal force N at the threads and the circumferential force P. Imposing force equilibrium in the horizontal and vertical directions in much the same way that we use them in our I-beam leveling problem, and using the fact that the tangent of psi as rise over run is L, the lead over the circumference based on the mean diameter, we can solve for P and then define the torque required to perform the operation as the product of P and the fastener radius, which would be half the mean diameter. This results in the following expressions for tightening torque, lower left, and loosening torque, lower right. I'd like you to note two things about these expressions. First, the expressions for tightening and loosening torque are asymmetric. We require less torque to loosen a fastener than we use to tighten it. And second, friction is a double-edged sword. The lower the friction coefficient, the less effort will be required to tighten the fastener, but the more likely the fastener will unwind itself without any loosening torque needed. We want the fastener to stay in place after we remove the load. That is, we want the fastener to be self-locking. But if we make the pitch of the threads too steep and friction too low, the fastener won't stay in place. As difficult as it may be to believe, there is an entire division of the American Society of Mechanical Engineers, that is, ASME, devoted to codes and standards for fasteners. Those of you choosing to major in mechanical engineering will learn far more about this in the future. For now, we turn our attention to problems involving slip on more than one surface.